So we had the proportion of students who live off campus. We made a claim about it, that it is less than 68%. So the null is just 0.68. That is our reference point. The alpha that we want is 0.01. P hat is 0.65, n is 6. And we found the test statistic, which is simply n multiplied by p hat, which is 4. And we ended up showing that there is not enough evidence to support the claim H1. Assuming the large sample approximation holds true, most likely that this is not going to hold true. We can find the test statistic B star as n p hat minus n p naught divided by square root of n times p naught times 1 minus p naught. Yes, the mean divided by the variance. If you divide by n, this formula will produce to p hat minus p naught divided by square root of p naught times 1 minus p naught divided by n. And if you closely observe that formula is the formula for a test statistic in a test for proportion. With a small difference, you would have used p hat in 2023. But we use the null version, so p naught instead of p hat. There are two different types. This is one of those two. This is what we call the score statistic. But would the answer be significantly different if you use p hat instead of p naught? The conclusion will be pretty much the same, more or less. But p naught is what we use in this case because we are doing it under the assumption of the null. We are assuming the null distribution. Are we clear? So these two are equivalent. So if you intend to use B directly, then you would use that formula. But if you want to use the sample proportion directly, you would use that formula. But it is a matter of choice. How would I go about this? If the problem gives you the proportion, we'll just stick to the proportion, right? If the problem gives you the number of successes, we'll stick to this. And someone tell me as to why. Do you follow my question? Is the problem, in this case, it gave you 65% of whatever set. So the proportion is given. So I'm just going to stick with this version. But if the problem gave 3 out of 6 students, I would go with this one. That is nothing but B. All X number of successes. But I just want to know why I make that difference and use it in different ways. In this problem, which one would you use? The first one. Why? I already have B, okay. But I already have P hat too. So this or that, yes.
Is that value closer to NP?
This is closer to NP naught.
So you're getting a small value.
But P hat is close to P naught also.
So I mean, like, when you ask between the difference between if distribution was 4
Oh, if it was 4 out of 2 number of successes,
So
then
the
you use
difference
this.
between the assumed probability and probability is actually not the same.
Okay. Well, I will use this one in this case because that value is given in the problem, rest is given in the problem. No rounding took place here, correct? But if I use this version, I've rounded B, correct? So I've introduced rounding already in my test statistic. So sure, would the answer be significantly different? No, they're not going to be. But this is an approximated version because I've approximated B. So in this problem, of the 2, I'd rather go with that because I don't have to round. I'll just round at the very end. Anytime you round, you are actually introducing error. So B star is the standardized test statistic. So 0.65 minus 0.68 divided by square root of 0.68 multiplied by 1 minus 0.68, 0.32 divided by 6. Numerator. And that's the denominator. What do we get? So that's the add. Now, if you didn't use rounding at all, in other words, you kept the number as is without rounding, you could use either. Right. The only reason why I'm going with this is because I've rounded, but you can use either if you use the exact value thing. So I end up getting negative 0.1575. That's my bell curve. 0 right in the middle, and that's where we have H0. That is our reference point. The rejection region, it should be on which side? Left or right? Left. Left. Why is that?
That's an alternative hypothesis.
The alternative is P less than 0.68, pointing to the left. Easier way to remember that way. So this is a left tail test. And we are going to make use of that area under the curve to find that critical value. What would the area under the curve be? Or what is it?
What's there? Yeah.
Go ahead.
No, because I forgot what needs to be on top, but the integral from negative infinity to.
Negative infinity to this point. I want to find this point, so I'm going to make use of that area. What is that area in this problem?
0.05.
0.05.
0.05. 0.05.
0.05. He's kind of getting there. What's given in the problem? Is 0.05 given in the problem or 0.01?
0.01.
0.01. And naturally, this number has to be negative. That critical value is below 0. How do we find this? Showed you last time.
Calculator.
Use the calculator. We have inverse norm. And we want to type in the area below. The area below is given in the problem. It is 0.01, followed by the mean and standard deviation. And that is 0.01. Critical value C star because it is an approximation, not the exact critical value. And what is that? Negative 2.38.
It's negative 2.33. That's rounded though.
Yeah, it's negative 2.32 exactly. So that critical value is negative 2.33. The test statistic that we found, the standardized test statistic, is negative 0.1575. Whereas negative 0.15759,
Before.
right here somewhere. Did the test statistic fall in the rejection region? No. Should we reject the null? No. We do not reject null. We don't find enough evidence to support the alternative. The exact same conclusion like the one we had last time. The next step is to find the p-value. So again, second vars, you'll find inverse norm, always the area below, so 0.01, followed by mean, followed by standard deviation, enter. That's the value we have. Now, p-value in this case is different from last example, the example that we did last week, because that was a right-tail test. This is a left-tail test. For a right-tail test, the p-value is the area above the test statistic. For a left-tail test, it is the area below the test statistic. Good. Even before you start the problem, do you expect this number to be bigger than 0.01, in a sense bigger than 1% or less than 1%? Less than 1%.
Bigger.
Bigger? Make up your mind. Is it big? Is it small? Why is it less? Area below the test statistic. So when in doubt, I always recommend that you draw it out. Why? Why is it bigger?
The area from negative 0.15 would be bigger than the area behind 0.01.
So that point is right over there. And I'm looking for the area below. So the area below would be all of that. And clearly the area in blue is bigger than the area in red. And the area in blue is the p-value. So how do we find the p-value? Second box, number 2. We start at negative infinity because it's the area below. So negative, second comma, 99. Go all the way up to the test statistic because it is below, area below the test statistic. Negative 0.1575. Mean 0, standard deviation 1, enter. 0.4374. So p-value, area in blue, bigger than the area in red, which is alpha. Naturally, p-value here is 0.4374. 0.4374 is bigger than 0.01, the alpha value that's given in the problem. So should you reject the null? You only reject the null if p-value is less than or equal to alpha. So same conclusion, do not reject null. Now, what was the p-value in our exact test last night?
The same example.
Yeah.
The original was 0.68, right?
Yes, but using the binomial test, we came up with the p-value. We added the probabilities. I believe it was 0.7 something.
0.07273.
0.7.
I don't think I ended up adding them up. 0.087.
We had the binomial values generated last time. We saved it to list two. And since it is less than or equal to 4, b is 4. So that's that, and that. And what did we get? Should be 0.7 something. Oh, it's 0.7. Oh, you can try again. Just add all the probability values less than or equal to 4.
24,
0.6240.
6224.
Oh, 6224. Well, the exact p-value is 0.6224. The approximate p-value is 0.4374. The exact test tells us, well, if you ignore what the data says, and I've rejected the null, the probability that I'd be making a type 1 error is 62.24%. The approximate test tells, the last sample approximation tells us, well, if you ignore everything, you rejected the null, the probability of a type 1 error is 43.74%. Either way, should you reject the null knowing that you'd make an error of the probability of error is 43%? No. 62%? Absolutely not. Good. Does that make sense? So, even though when we started the problem, the sample proportion was certainly less than the claim that was made. But just because the sample proportion is less than the claimed value doesn't make it true. Reason being, we have to account for randomness and variation in population. So we want to establish if it is significantly less than 0.68, based on our test, and it's not significantly less than 0.68. Good.